Okay, here we are. We're going to take a look at the last of the free response questions, and this one is a rotational one. In this case, we have a heavy platform, kind of reminiscent of that disc that you bolted to the rotational motion sensor, and it's rotating around a vertical axis, and there's a smaller wheel underneath, a distance d away from the vertical axis, and it's going to rotate and apply some sort of force or torque. The smaller wheel has a radius r, and so we read the words here. A horizontal circular platform with rotational inertia IP. Okay, rotates freely. IP freely without friction on a vertical axis. A small motor driven wheel that's used to rotate the platform is mounted under the platform and touches it. The wheel has radius small r and touches the platform a distance d from the vertical axis of the platform as shown above. The platform starts at rest and the wheel exerts a constant horizontal force of magnitude F tangent to the wheel until the platform reaches an angular speed omega p after time delta t. During time delta t, the wheel stays in contact with the platform without slipping. Okay, cool. First thing they're going to ask, and again, this is usually the softball question, the start leading you down the path question. Derive an expression for the angular speed of the platform. Express your answer in terms of these things and physical constants as appropriate. So we have IP, little r, capital D, F, delta T, and physical constants. All right, so we're deriving an expression for the angular speed. This is going to be part A. And in part A, we're going to derive an expression for the angular speed. Now, the angular speed at the end of this process is going to be the angular speed at the beginning of this process plus the angular acceleration times the time interval delta t. That's pretty clear. So all we really need to do is find out what alpha is going to be, and we should be in shape. So where do we get alpha? Well, alpha comes from torque. So there's this force underneath the platform. As seen from above, the platform looks like this, and there's a axis in the center. And somewhere underneath there is a little wheel, and that little wheel is exerting a force, constant force F, at a distance d away from the axis. There we go. Oh, gardeners must be here again. So that's going to create a torque. So we're going to say that the torque created by that force is going to be IP times alpha. That's great. That means that alpha is the torque created from that force divided by IP. Now, what is the torque? Well, the torque, because the force is acting at a right angle to the distance away, the lever arm, then it's just the product of the force and the lever arm. So this is really a simple expression for the torque, and now we can put that into our expression up here and decide that omega p, the final speed, is going to be F d delta t all over IP. And that's in terms of things that we're allowed to use. So I believe that's a finished product answer. And it wasn't too bad. That was using the rotational kinematics equations. Now let's have a look at what the next question is as they ask. Part B, determine an expression for the kinetic energy of the platform at the moment it reaches angular speed omega p. Express your answers in terms of, okay, this is all the same stuff that we're allowed to express our answer in terms of. So we're looking for the kinetic energy at the end of the process. Just for clarity, let's change colors here. Okay, B. Well, we want the kinetic energy, and we want the kinetic energy of rotation, which is, by analogy, 1/2 I omega squared. That's the general formula, but now let's be specific. We have 1/2 IP, and we have that expression that we did earlier, FD delta t over IP quantity squared. All right, 2 on the bottom. Looks like we're going to have IP squared on the bottom, but 1 IP on the top. So on the bottom of this fraction is going to survive 2 IP. On the top of the fraction is going to be an F squared d squared delta t squared. Now, if you want to put all this in parentheses and square the whole darn thing, I approve of this message. But this is an expression for the kinetic energy of rotation when we reach our final velocity. Again, fairly straightforward. I'm kind of excited that this is a rotation question, but they haven't really challenged me yet. Let's look at part C. And of course, we can see if we look ahead that there's another picture. So our wrinkle is coming after C. Okay, C. Derive an expression for the angular speed of the wheel omega w when the platform has reached angular speed omega p. Express your answer in terms of d, r, omega p, and physical constants. It's a slightly different set of variables you're allowed to use. But we need to think about this because they're asking about the wheel. Okay, so when this thing at the top here, whoops, let me pull it down. When this thing reaches the speed omega p, then this wheel is going to have a different speed, omega w. And they're not going to be the same. But what is going to be the same? Well, if we go back and look at this without slipping concept, and also the idea that when two things are touching, like gears or what have you, then what's really going on is that the velocity of p will be equal to the velocity of w. And so I'm going to use that idea. So let's change to another contrasting color for clarity here. Maybe we'll write some words. Platform and wheel moving at same linear velocity. So that means the velocity of the platform and the velocity of the wheel where they touch are going to be the same. Now, linear velocity is actually angular velocity times r. So the angular velocity of the platform times the radius at which it is being touched equals the angular velocity of the wheel times the radius at which it is being touched. And now we've got our ratio here. We've got that omega wheel is going to equal omega p times the ratio d over r. Looks like that little wheel is going to be hustling. Now, that is the appropriate thing. Those are the appropriate variables. You know, we could have put in our expression for omega p here, but then it wouldn't have been in the correct. I don't know if they would dock you points for that had you put the FD, delta T, and IP in there. But paying attention to what the question is and boxing up the allowable variables is really going to help focus you on what you're supposed to do here. Okay, so we jumped through their hoops and we answered their questions about the original situation. So now it's time to deal with the wrinkle. And let's take a look at the wrinkle. They have something above, and this thing is spinning below. This is the same platform as before. Looks like they're going to take this platform, they're going to get it spinning, like we did before, then drop this guy on it. And let's read. When the platform is spinning at an angular speed omega p, the motor-driven wheel is removed. Okay, so that's not a problem. Student holds a disc directly above and concentric with the platform as shown above. The disc has the same rotational inertia IP as the platform. The student releases the disc from rest, and the disc falls onto the platform. After a short time, the disc and platform are observed to be rotating together at an angular speed omega f. Okay, so if I imagine what's going to happen here, we're going to drop something that has a moment of inertia IP onto something that's already rotating that has a moment of inertia IP. And they're going to, this thing is going to skid and slide underneath this thing, and the top thing is going to speed up, and the bottom thing is going to slow down, and eventually they're going to reach the same speed omega f. Okay, I don't want to answer that phone call. So this is kind of like the ice skater situation in the sense that, she had her arms out. She had one a moment of inertia, She brought them in and had a smaller moment of inertia, and suddenly she sped up. This is the opposite thing. This is where we're going to add moment of inertia, so the thing's going to slow down. So let's go ahead and go back to the black pen, and I think I can get this on the bottom of the page here. My page is kind of sticking. Here we go. So for part D, what are we going to conserve here? Certainly can't be energy because there's going to be some friction between these two as the top one speeds up and the lower one speeds down. But much like with the skater, we can definitely conserve angular momentum. So the angular momentum at the beginning is going to be the same as the angular momentum at the end. And so let's see. By the way, the question, I didn't really draw your attention to the question. It says, derive an expression for omega f. Express your answers in terms of omega p, I, and physical constants as appropriate. So they really are saying don't plug your stuff in. Let's just see what we can do here. Omega p, which is the original speed, times ip, which is the original moment of inertia, is going to equal the new moment of inertia, which is twice IP plus IP, and that's going to be times omega F. This couldn't be more trivial. Omega F is going to be equal to, well, it's going to be equal to omega P IP over 2IP, giving us omega P over 2 equals our omega F. Wow, they're really taking it easy on us. I wonder why that is. Why are they not giving us the full oh, here's why. Take a look at this. There are 2 more pages of questions. One page is a graph, so obviously we're going into the lab, and the other page has questions E, F, and G. I see why they took it so easy on us thus far. I'm going to save this piece of paper on the side. I can't show it to you all the time, but we need a new paper for what's going to happen to us for the rest of the problem. I suspect we're also going to need a ruler. But let's have a look at this page here. This is the next setup. So a second wrinkle, a double wrinkle problem, a zig and a zag. A student now uses the rotating platform, and now they give you a number. Okay, so it looks like we're going to be computing things with numbers from now on. To determine the rotational inertia IU of an unknown object around a vertical axis that passes through the object's center of mass. The platform is rotating at initial angular speed omega I. That's another omega altogether. When the unknown object is dropped with its center of mass directly above the center of the platform and the object are observed to be rotating together at an angular speed omega F. Trials are repeated for different values of omega I, and a graph of omega F as a function of omega I is shown on the axis below. Okay, so we're kind of doing a general experiment. Before we dropped on an identical cylinder or disk, and so the moment of inertia went up by a factor of 2, but now we're going to drop random stuff on, Hot Wheels, cars, Star Wars figures, whatever you got in the house. We're going to be dropping that on at various values of omega I versus omega F. And so I'm looking at this graph and I'm saying, okay, this is a graph of omega F versus omega I. The AP test is pretty careful to always put the variable that you have control over. This is the one you control, and this is the one you observe over here. Doesn't necessarily mean that this is going to be the way we need it. Once again, we've learned a number of times that when we find the slope, we often need to invert the slope. But let's see what happens here. I'm looking for a best fit line, one that goes through the points but doesn't necessarily touch the points. I'm going to call it for this line right here. Let's have a look at this when we're done and see what we see. Does that seem to go through the points? I've got points above, I got points below. Man, I'm pretty pleased with my ability to draw a best fit line, particularly with a piece of cardboard that is not transparent. You love it when you get a transparent ruler because you can see the points that would otherwise be obscured. But as I've said many times, it's drawing best fit lines by eye is an amazing process. You're very close to the perfect answer. I see a point here that I could use to find the slope, and I'm looking for another. Boy, this one looks really good too. All right, I'm going to go with those, and let's just quickly find the slope. I'm not 100% sure I'm going to need to do this, but I am 99.9% sure. Okay, so rise over run. We're starting here, and if this is so this is 0.6 radians per second, and then this up here looks like about 2.8 radians per second. So my rise is going to be 2.8 minus 0.6. My run is going to be, now run, this looks like 2, and this looks like 6.25. So 6.25 minus 2. All right, let me get the calculator out and hit this and see what we get out of that deal. We're going to have 2.8 minus 0.6 equals, and we're going to divide that by parentheses. So don't do that. 6.25 minus 2. Okay, I'm getting a slope of 0.518 out of this deal. Does that make sense? Yeah, look, it looks like a slope of about 1 to me, but then this goes up to 5 and this goes up to 10, so slope of a half makes more sense. May need that later. Let's see what they do to us here. Part E. On the graph of the previous page, draw a best fit line for the data. Check. Using a straight line, calculate the rotational inertia of the unknown object about a vertical axis. Wow, they're asking us to do like the entire experiment right here. So E2 is pretty much everything. And what we're going to do is we're going to use the model that we had before of our conservation of angular momentum here, and we're gonna. Let's move this down. There we go. I can make this more continuous. E2. All right. So what we're gonna do here is we're gonna say that L equals L prime. That means that IP times omega I, the starting thing, is going to be IP plus IU times omega F. Now, let's see. We're trying to isolate IU, so let's get omega F onto the other side. So let's go over here. We're going to say that IP times the ratio omega I over omega F equals IP plus IU. We are one step away. Sorry that looks like an O. It's a U. One step away. We should just go ahead and say that IU is going to be equal to IP times the quantity omega I over omega F minus 1. All right, what I've done is I brought the IP to the other side and factored it out. And that's interesting right here because this is the inverse of the slope that we found. So I guess if we go back here and we could say the inverse of our slope, and this is still on my calculator screen, so I can just hit the 1 over button. Inverse of our slope is 1.93. Okay, good. Let's go ahead and do that. Now we can find, they want a numerical value. Oh, we can give them a numerical value. That's because IU is going to be the 3.1 kilogram, whatever, times 1.93 minus 1. So I'm going to take 3.1 and I'm going to multiply it by 0.93, and I'm going to get an IU of 2.88. We should probably just go 2.9 to keep the same number of sig figs as they had there. In my previous solution, I didn't even write down the units. Okay, or the number. Okay, so there we go. Now we're cooking with gas here. Let's have a look at our boom. Okay, so now we're on to F, and we're getting close to the 20-minute mark. I like to get these things done in less than 20. The kinetic energy of the spinning platform before the object dropped on it is Ki. The total kinetic energy of the platform object system when it reaches speed to omega F is Kf, which is the following expressions is true. Well, absolutely. Kf has to be less than Ki. All right, and that's because Kf must be less than Ki. And there's a couple different reasons. One is you could say that friction sped up the unknown object, or you could say that this is an inelastic collision. Actually, it's a perfectly inelastic collision, isn't it? Because they stick together. Perfectly inelastic collision, and that means that energy is lost. There's a lot of different things you could say to explain this, but that is absolutely the case. Kinetic energy will not be conserved in this collision. It will be lost. And that brings us to our final thing we're going to do here. One of the students observes that the center of mass of the object is not actually aligned with the axis of the platform. Oh, come on, man. Is the experimental value of IU obtained in part E greater than, less than, or equal to the actual value of the rotational inertia of the unknown object about a vertical axis that passes through its center of mass? Okay, let's think about this. Now, if you drop this thing onto the platform and it's off center, then we would have to calculate its moment of inertia by taking the moment of inertia through the center of mass, which we were originally calling IU, and adding to it a term of m times d squared. And this is the parallel axis theorem. So that means that the number that you're going to get is absolutely going to be the correct number plus something. Mass has to be positive. Distance squared or location squared always positive. So the number you're going to get is going to be higher. So how do we answer this question? We say that the answer you would get would be greater than, and I would justify it with this equation, or just mention that the parallel axis theorem means you have to take the rotational inertia around the center of mass and add something to it. The point is, it's always easier to spin something around its center of mass than it is some other point. So this is the solution to the fairly complicated rotational question. I just want to point out that on the Google Classroom, I did a little more research about what will be on your test, and the only thing that I'm not clear about is whether drag and the associated differential equation will be part of your test. All right, we're going to call it here. That way I'm under the 21-minute mark. Talk at you later.